All right, Ski. Ultimate frustration. Um, I had to actually record that last video, I think, 3 times. And then when I went to upload it, it did something funny. So I ran it through an editing piece of editing software and changed the format. So I apologize if that last video was in any way grainy or what have you. So we're going to continue on, and we're going to do an example of something that's very akin to the ballistic pendulum in that it uses conservation of momentum and conservation of energy. But this one is actually going to be conservation of energy, then conservation of momentum, then conservation of energy. And here's the situation. So Tarzan has got himself into a spot of bother here. He is being chased by a crocodile. Let's put him on this side. I seem to have more room for a crocodile on this side. And if you laugh at my crocodile picture, I will understand, because that's a crocodile in my world here. Okay, and Jane is going to rescue him. So Jane happens to be standing at the top of a 5-meter tall cliff, and she has one of those patented Tarzan and Jane vines that she can swing on, and it is also a 5-meter vine, so that means that she can swing down, and then she's going to pick up Tarzan, and then together they're going to swing up, and hopefully, I don't know how you draw Tarzan and Jane together without making it look like a pair of scissors. Hopefully they're going to be able to get to safety on this little rise that's 2.5 meters over here. So what we want to do is we want to figure out what's going to happen when Jane swoops in, grabs Tarzan. How high are they going to swing? So in this situation, we're going to find out how high they're going to swing. So H equals, Now we need some information. Jane is a little more svelte, and she is 50 kilograms. Tarzan is the traditional buffed out superhero type of Tarzan, and he is 75 kilograms. One moment, folks. I have to let my dog in. She's making noises at the door. Oh. When I start narrating these videos, excuse me, girl. I don't know. She just likes to be in the room when I'm talking. She's the only person or the only creature in the world that wants to be in the room when I'm talking. Hey, that's a joke there. Okay, so we're going to have to look at this. Conservation of momentum, conservation of energy. First thing is first, we're going to do conservation of energy to figure out how fast Jane is going when she swings down here. So let's do a quick picture. We have Jane up here, and then Jane is going to be down here and moving very fast. So pretty clearly, she goes from having potential energy to having kinetic energy. Well, there we go. Potential energy that she had at the top is going to equal her kinetic energy when she gets to the bottom. Now, this is a 5-meter long vine, so 5 meters here, 5 meters here. So pretty clearly, she has m times g times h at the top, and she will have 1/2 mv squared at the bottom. Her mass is the same, cancels out, and we'll multiply both sides by 2, 2gh equals v squared, and her velocity will be square root of 2gh. In this example, that is the square root of 2 times 10 times 5. Now, 2 times 5 is 10. And 10 times 10 is 100, and the square root of 100 is 10, so her velocity will be 10 meters per second when she gets to the bottom. Alrighty. I apologize for the lack of focus. My webcam seems to be confused as to where things need to be focused. Alright, so now the next thing is to deal with the conservation of momentum. That is, when she goes to pick up Tarzan, her mass is going to increase. This is very much like the bullet impacting into the block of wood in the ballistic pendulum. So in that case, the momentum total before equals the momentum total afterwards. Oh, and I've used blue again. Oh well, so much for color. Now, before she grabs Tarzan, and I'm looking at this picture right here because we have them coming together, and then afterwards there's going to be the two of them crossed like that. Before she hits Tarzan, she's the only one that has momentum, so it's the mass of Jane, let's put a J here, times her velocity. But afterwards, we're going to have the mass of Jane plus the mass of Tarzan. And, oh, yeah, like these don't look the same. Times V prime, which is going to be some velocity afterwards. Okay, quickly. Jane's mass is 50. Her velocity was 10. Together, it's 50 plus 75, and then we'll figure out what their velocity is. So 500 equals 125 times v prime, or 500 over 125 equals v prime. And I've got a calculator handy. So we have 500 divided by 125 equals, and that's 4. So she's doing 10 meters per second. She grabs Tarzan, and they together slow down to 4 meters per second. All right, next. They together will swing up, and we'll see how high they're going to swing up. In this case, it's conservation of energy. And the kinetic energy that the two of them have will turn into potential energy, and we'll see how high they swing up. So 1/2 of their combined mass, m plus m, I'm going to use the big M, little m notation I used last time, times their velocity, which is v prime squared, is going to equal their combined mass, m plus little m, times g times h. Okay, now the combined mass, the 125 kilograms of combined mass, actually cancels on both sides. So we need 2 times their velocity prime squared divided by g, and that will give us h. So I've canceled these two, and I've divided both sides by g. So 2 times this 4, but the 4 gets squared, divided by 10 equals how high they're going to swing. Okay. 2 times 4 squared. Now 4 squared is 16, and 2 times 16 is 32. Divided by 10 equals h, and that equals 3.2 meters. So it looks like Jane can successfully rescue Tarzan from the clutches of this alligator by swinging down and with quite some impact or impulse, grabbing him and swinging up. They'll be able to go higher than the 2.5, so they'll probably go up, and then on the way back down, they'll let go of the rope and drop onto the cliff over there, and perhaps stick their finger out, or their tongues out, or something out at the alligator, and they'll call him Boots.